The sterile concrete floor of the Kummersdorf Proving Ground echoed with the sound of boots on February 22, 1943. A group of German automotive engineers gathered around a peculiar sight, an American M4 A1 Sherman tank, still bearing the name War Daddy II, stenciled across its hull in fading white paint. Captured just days earlier from the 1st Armored Division near Spitla, Tunisia, the tank had been driven 350 kilometers to Tunis, a 4.5-day journey, then shipped across the Mediterranean to the heart of the Third Reich. Now it sat under the gray German sky, surrounded by men whose professional lives had been spent perfecting what they believed to be the world's most sophisticated armored vehicles. What these engineers were about to discover would shake the foundations of everything they thought they knew about tank design. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Germans approached the Sherman with a mixture of curiosity and barely concealed contempt. They had been told that American tanks were crude, hastily assembled products of a nation more interested in automobiles than warfare. The United States had entered the war woefully unprepared in terms of armored doctrine and technology, and the Germans knew it. When France fell in May of 1940, America lagged far behind every major European power in tank development. The Sherman itself had been rushed into production in October of 1941, designed and deployed faster than any tank in modern warfare. How sophisticated could such a weapon possibly be? The chief engineer at Kummersdorf, a man named Klaus Richter, whose career had been built on the precise tolerances of German manufacturing, walked around the Sherman with a measuring tape and notepad. Other engineers followed, stenciling armor thickness measurements and angle calculations directly onto the tank's hull in white chalk. 75 millimeters at 12 degrees on the glacis, 51 millimeters on the turret front. They recorded everything with Teutonic precision, photographing the tank from every conceivable angle. In the background, barely visible in period photographs, sat Germany's answer to Soviet armor. The Panther tank, a 44-ton masterpiece of engineering complexity that had debuted at Kursk 8 months earlier. The irony of what was about to unfold would have been almost comedic if the stakes weren't measured in thousands of human lives. German tank philosophy in 1943 represented the apex of traditional engineering thinking. More armor meant better protection. Larger guns meant superior firepower. Heavier transmissions meant greater durability. The Panther embodied this philosophy completely. Its KWK 42-75 millimeter gun could penetrate a Sherman's frontal armor at ranges exceeding 1,500 meters. Its sloped frontal armor, inspired by the Soviet T-34, was virtually immune to most Allied anti-tank weapons at normal combat distances. On paper, the Panther was everything a tank should be: powerful, well-protected, technologically advanced. But paper specifications told only half the story, and sometimes not even the most important half. The Panther's Maybach HL230 V12 engine produced 700 horsepower, an impressive figure for a tank of its size. But that engine, operating at the bleeding edge of what German metallurgy could achieve with increasingly scarce high-quality alloys, had a service life of approximately 1,000 kilometers under ideal conditions, about 621 miles. The transmission, a marvel of German engineering with 7 forward gears and a complex steering system that allowed for different turning radii in each gear, began experiencing failures almost immediately. About 5% of Panthers broke down within the first 100 kilometers of operation. 90% suffered transmission failures within 1,500 kilometers. The final drive, the component that transferred power from the transmission to the tracks, was the Achilles heel of the entire system. To reach it for repair, mechanics had to disassemble and lift out the entire driver's compartment and transmission, an operation that required specialized equipment, trained technicians, and at minimum a full day of work, often longer. A report from the Eastern Front in late 1944 noted that prior to an offensive, the Germans had 500 defective final drives on Panzerfues, 370 on Panthers, and roughly 100 on Tigers. General Thomas Tommel explained that in such circumstances, an orderly utilization of tanks was simply impossible. The troops were losing their confidence. In some situations, they abandoned the entire vehicle just because of final drive failure. This was the German engineering philosophy that Klaus Richter and his team at Kummersdorf believed represented the pinnacle of tank design: sophisticated, powerful, and increasingly unreliable. Now contrast that with what they found when they started opening up the Sherman. The first thing that struck the German engineers was how easily the Sherman's components came apart. The entire engine, a 4 GAA 8-cylinder V8 producing 500 horsepower, could be removed and replaced in approximately 2 hours by a field maintenance crew with minimal specialized equipment. Not 2 days. Not with a gantry crane and half the drivetrain disassembled. 2 hours. The Americans had designed the Sherman with a simple philosophy. Soldiers in combat don't have time for complicated repairs. The engine compartment was spacious, with clear access to every major component. The transmission was separate from the final drive, but connected by a straightforward drive shaft. If something broke, you could reach it, diagnose it, and fix it without dismantling half the tank. Parts were standardized across different Sherman variants to an almost absurd degree. Turrets, final drive housings, even entire engines could be swapped between different models with minimal modification. One German engineer, examining the Sherman's Continental R975 radial engine variant, noted in his report that even this more complex power plant was easier to troubleshoot and repair than comparable German systems. Another remarked on the Sherman's use of common automotive components, parts that any American mechanic who had worked on trucks or cars would immediately recognize. The simplicity wasn't a sign of crude design. It was deliberate engineering for a specific purpose: keep the tank running under combat conditions, where perfect workshop conditions don't exist, and replacement parts might not arrive for weeks. The Germans tested the Sherman extensively through the spring and summer of 1943. They measured its armor, tested its gun, evaluated its speed and maneuverability. But the most telling discovery came when they simply started using the captured Shermans as recovery vehicles. German Tiger and Panther units in Italy began converting captured Shermans into Panzers, armored recovery vehicles, by removing the turrets and using them to tow broken-down German tanks. This became a source of bitter irony on the battlefield. It was terribly frustrating for German crews to get a Panther, the Panther-based recovery vehicle, in place to try and tow a broken-down Panther, only to have the recovery vehicle itself break down. But a Sherman-based recovery vehicle? That just kept running. A British intelligence report from March of 1944 stated that Germans in Tiger units in Italy loved the captured Shermans they had converted to recovery vehicles because they were so reliable. Think about that for a moment. German soldiers, operating what was supposedly the finest armored fighting vehicle ever designed, the Tiger tank, preferred to use captured American equipment for recovery operations because their own vehicles couldn't be trusted to complete the mission. The philosophical difference between American and German tank design was becoming brutally clear, and it wasn't a difference that favored the Germans. American designers had asked a fundamentally different question than their German counterparts. The Germans asked, "How do we build the most powerful tank possible?" The Americans asked, "How do we build a tank that will still be fighting 3 months from now?" These seem like similar questions, but they led to radically different engineering choices. The Sherman's 75-millimeter gun was adequate rather than exceptional. Its armor was good enough rather than impenetrable. Its engine was reliable rather than revolutionary. Every design choice prioritized operational availability over theoretical superiority. The Americans understood something the Germans were only beginning to learn. A tank that's being repaired can't fight, and a tank that can't be repaired at all is just scrap metal. By mid-1943, the Sherman's average service life was estimated at 1,500 miles, approximately 2,400 kilometers. Soviet forces using Lend-Lease Sherman tanks determined their lifespan to be between 2,000 and 2,500 kilometers, or about 250 to 300 hours of operation. This was comparable to the T-34 and dramatically superior to German armor. The Ford GAA-powered M4A3 variant participated in a survival race in 1943. On average, these engines worked for 255 hours before major servicing was required. One failed after 87 hours, but that was an outlier. In extended testing during the winter and spring of 1944, one Sherman covered 2,097 miles in 203 hours and 25 minutes of continuous operation. Compare this to the Panther. After the disastrous debut at Kursk in July of 1943, where nearly 50% of the initial 200 Panthers deployed were out of action within days due to mechanical failures, the Germans launched an intensive improvement program. By March of 1944, General Heinz Guderian proudly reported to Hitler that the Panther's engine service life had increased from 700 to 1,000 kilometers. He noted that final drive breakdowns had ended, and transmission and steering gear failures were now within an acceptable range. Damning with faint praise barely covers it. Within an acceptable range meant the Panther was still breaking down at rates that would have been considered catastrophic for American or Soviet armor. The availability rate of Panther tanks, the percentage that were actually operational at any given time, went from a dismal 37% at the end of 1943 to 54% by late 1944. The Germans considered this a success. Meanwhile, Sherman availability rates regularly exceeded 95%. The engineers at Kummersdorf couldn't help but see the truth in the numbers. They were professionals, after all, men who understood mechanical reality, even when it contradicted national mythology. The reports they filed were matter-of-fact, clinical, free of the propaganda that colored so much of German military assessment. They noted that the Sherman was well-built, reliable, and comfortable. They praised its automotive engineering. They recognized that American tank crews operated in vehicles that were easier to maintain, easier to repair, and more likely to be running when they needed to fight. What they couldn't say in official reports, what would have been professionally and perhaps personally dangerous to articulate, was that this represented a fundamental failure of German engineering philosophy. The Germans had spent the 1930s and early 1940s building tanks that were masterpieces of precision engineering, tight tolerances, complex systems, components manufactured to exacting specifications that required specialized factories, skilled craftsmen, and increasingly scarce materials. They had built tanks that performed brilliantly when everything worked perfectly, but fell apart when conditions became difficult. The Americans, by contrast, had built tanks that were good enough when everything worked perfectly, but kept fighting when conditions became difficult. Which is to say, they had built tanks for actual war rather than ideal conditions. A long-distance service trial conducted in Britain in 1943 compared diesel and gasoline Shermans to Cromwell tanks and Centaur tanks. The British officer commanding the trial concluded, "They are utterly reliable. I do not think they are quite as good as the Cromwell across the country, when they are running on rather worn rubber tracks and the going is greasy. Neither does one get as smooth a ride, but they appear so infinitely superior in every other way, particularly in reliability with a minimum of maintenance, that this cross-country consideration is completely overweighed. Utterly reliable. Those two words appeared again and again in Allied assessments of the Sherman. Not powerful, not sophisticated, not technologically advanced. Reliable. The German engineers at Kummersdorf understood what this meant, even if the implications were uncomfortable. You could have the best gun in the world, but if your tank broke down on the way to the battle, that gun fired exactly 0 rounds at the enemy. You could have impenetrable frontal armor, but if your transmission failed after 200 kilometers, that armor protected nothing except immobile steel. You could design the most sophisticated steering system ever fitted to an armored vehicle, but if it required a full day and specialized equipment to repair, you just created a logistics nightmare. And logistics, ultimately, determined who won wars. By mid-1944, the United States had produced approximately 30,000 Sherman tanks. The Sherman wasn't just one vehicle, it was an entire industrial ecosystem. Multiple manufacturers, multiple engine types, multiple variants, but all sharing common components and design philosophy. Ford, Chrysler, General Motors, and other companies that had spent decades perfecting mass production techniques for automobiles turned those same techniques toward tank production. Assembly line efficiency, standardized parts, modular design, quality control that emphasized consistent performance rather than perfect tolerances. Germany, by contrast, produced approximately 6,000 Panthers and 1,800 Tigers through the entire war. These tanks weren't mass-produced. They were essentially hand-built. Some of this was due to Allied bombing of German industry. Much of it was due to the complexity of the designs themselves. Building a Panther required specialized facilities, skilled labor, and components that couldn't be easily substituted or simplified. The interleaved road wheel system, that distinctive overlapping pattern of wheels that gave German tanks their superior soft ground performance, required wheels machined to precise specifications. In winter on the Eastern Front, mud and snow would pack between the wheels and freeze overnight, immobilizing the tank until crews could painstakingly chip away the ice. This sometimes took hours. The Sherman's road wheels were simpler, cruder, and kept working. The engineers at Kummersdorf were beginning to understand that American industrial philosophy represented something more sophisticated than they had given it credit for. The Americans hadn't failed to build a tank as complex as the Panther. They had deliberately chosen not to. They had looked at the requirements of industrial warfare, the need to produce vehicles by the thousands, maintain them under field conditions, repair them quickly, and keep them fighting across multiple theaters and terrain types, and designed accordingly. This was engineering sophistication of a different kind. Not the sophistication of tight tolerances and complex mechanisms, but the sophistication of system-level thinking. The Sherman wasn't just a tank. It was part of a comprehensive system that included production facilities, supply chains, maintenance protocols, crew training, and battlefield doctrine. Every component had been designed with this system in mind. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Chrysler A57 multibank engine exemplified this philosophy perfectly. This bizarre power plant consisted of 5 6-cylinder automobile engines mounted together on a common crankcase, creating a 30-cylinder engine that looked like it had been designed by a committee having a collective nervous breakdown. German engineers examining this engine would have considered it an abomination, a crude kludge that violated every principle of elegant design. But the A57 worked. More than that, it worked reliably. Chrysler Corporation sent an army of technical representatives into the field to train crews on maintenance. They redesigned parts based on feedback from actual combat conditions. The individual banks were solid, well-designed motors. The complication came only in mating them together. And because each bank was essentially a standard automobile engine, parts were readily available, and mechanics already knew how to work on them. The A-57 became, against all aesthetic sensibilities, remarkably reliable. British forces particularly loved Shermans powered by this engine, finding them more dependable than many simpler alternatives. The design was ugly, inelegant, and completely effective, which meant it was exactly what the battlefield required. German engineering couldn't conceive of such compromises. Or rather, German engineering culture had convinced itself that such compromises were beneath the dignity of proper design work. A tank engine should be purpose-built, optimized, refined. It should embody engineering excellence in every component. The fact that such engines were more expensive, more difficult to manufacture, more complicated to repair, and less available when needed. These were acceptable costs of achieving technical superiority. Except they weren't acceptable costs, not when you were fighting a global war of industrial attrition against opponents who could outproduce you 10-1. The Sherman's modularity extended to almost absurd lengths. Different variants used different engines. The Continental R9-75 radial, the Ford GAA V8, the General Motors 6046 diesel, the Chrysler multibank, even Caterpillar diesels for export models. This created logistical headaches. Mechanics had to know multiple engine types, supply chains had to stock different parts. But it also meant that American tank production was never constrained by shortages of any single engine type. Whatever power plant was available, you could build a Sherman around it. This drove German engineers to distraction. How could you maintain quality control with such variation? How could you ensure consistent performance? How could you even properly categorize such a weapon when individual examples differed so dramatically? The answer was that the Americans didn't care about consistency for its own sake. They cared about getting functional tanks to the front lines. If that meant some Shermans had radial engines and others had V8s, so be it. The important thing was that they all drove, all fought, and all could be maintained by crews who didn't need to be specialist mechanics. A German prisoner of war, interrogated by British intelligence in Normandy during the summer of 1944, revealed something that would have been unthinkable to admit in official German military circles. He explained that Panther tank drivers were specifically instructed to avoid using the auxiliary skid brakes for steering when possible, and to never attempt pivot turns except when absolutely necessary. The steering mechanism was so fragile, he said, that normal tactical maneuvers could destroy it. Think about what that means in combat. A tank commander spots enemy armor appearing on his flank. His tactical instinct screams at him to pivot the tank quickly, bring the gun to bear, engage before the enemy can fire. But he knows that if he orders a hard pivot turn, there's a substantial chance his transmission will fail, leaving him immobilized and defenseless. So he hesitates. He orders a wider, gentler turn that takes precious seconds. Seconds that, in armored combat, often determine who lives and who dies. The Panther wasn't a tank. It was a mechanical hostage situation where the crew had to negotiate with their own vehicle's fragility. The final drive problems were even worse. German engineers had designed the Panther's final drive for a tank that would weigh approximately 35 tons. The actual combat-loaded Panther weighed 44 tons. This 9-ton discrepancy, the result of adding armor, equipment, and combat necessities during development, meant the final drives were perpetually overstressed. They failed with depressing regularity, and when they failed, The repair process was nightmarish. First, the crew had to remove all the internal equipment from the driver's compartment. Then they had to disconnect the transmission from the engine. Then, and only then, could they lift the entire transmission assembly out of the tank to access the final drive. This required a specialized gantry crane or a Panther recovery vehicle. Even with proper equipment and trained mechanics, the job took a minimum of 8 hours, often much longer under field conditions. Contrast this with the Sherman, where final drive repairs could often be completed in under 2 hours without removing the transmission. American tank crews weren't mechanics, but they could perform basic repairs that would have required a German tank to be sent to a rear area workshop. The engineers at Kummersdorf documented all of this. They tested the captured Shermans alongside Panthers and other German armor. They measured, they calculated, they wrote reports. And in those reports, carefully worded to avoid explicit criticism of German design philosophy, they noted that American tanks prioritized ease of maintenance and automotive reliability in ways that German tanks did not. But here's what they couldn't say in official documents. The Americans had beaten them at their own game. Germany had spent a century building a reputation as the world's premier engineering nation. German precision, German quality, German innovation. These phrases carried weight across the industrial world. When you bought a German product, you expected it to be the best that current technology could produce. This wasn't just national pride. It was a fundamental element of German economic and cultural identity. The Americans, by contrast, were known for mass production, not precision engineering. American products were seen as adequate, accessible, affordable. They worked well enough for most purposes, but lacked the refinement of European craftsmanship. American automobiles were spacious and comfortable, but mechanically crude compared to German designs. American industrial products emphasized quantity over quality, standardization over customization. Or so the Germans believed. What the Sherman revealed was that the Americans had developed a different kind of sophistication, a sophistication of system design rather than component perfection. They understood that in industrial warfare, the most important specification wasn't how well a tank performed under ideal conditions, but how reliably it performed under terrible conditions. They recognized that maintenance in combat zones would be done by young men under fire with limited tools and no specialized equipment. They accepted that parts would wear out and need replacement. So they designed for easy replacement rather than trying to build components that would last forever. This was engineering maturity. The Germans were still designing for the peacetime proving ground. The Americans were designing for the chaos of actual war. Soviet tanker Dmitry Loza, who commanded Lend-Lease Shermans on the Eastern Front, later wrote about what impressed his crews most about the American tanks. It wasn't the armor or the gun. It was the auxiliary power unit, a small generator that could keep the tank's batteries charged without running the main engine. Soviet and German tanks required the crew to run the main engine periodically to charge batteries, wasting fuel and announcing their position to the enemy. The Sherman could sit silent for days, batteries fully charged, ready to start instantly when needed. Such a small thing. Such an obvious thing, really. Any engineer could have designed an auxiliary power unit. But German and Soviet designers hadn't thought of it, or hadn't considered it, important enough to add weight and complexity to their vehicles. The Americans had recognized that small conveniences multiplied across thousands of tanks, and months of campaigning created enormous tactical and logistical advantages. Loza also noted the Sherman's reliability and ease of maintenance. His crews could fix mechanical problems that would have sidelined a T-34 for days. They could swap parts between vehicles. They could diagnose issues without specialized training because American design made mechanical problems obvious rather than mysterious. The British ran extensive comparative trials in 1943, testing Shermans against their own Cromwell and Centaur tanks across various terrain and weather conditions. The results were unambiguous. While the Cromwell had some advantages in cross-country mobility on certain surfaces, the Sherman's overall reliability and maintainability made it the superior vehicle for sustained operations. British commanders chose Shermans for critical missions not because they were the most powerful tanks available, but because they were the tanks most likely to actually arrive at the battlefield in working order. This brings us back to Kummersdorf, and to the central question that the German engineers couldn't quite bring themselves to ask directly. If American tanks were so reliable and German tanks were so unreliable, what did that say about German engineering excellence? The answer, uncomfortable as it was, suggested that German engineers had optimized for the wrong variables. They had pursued theoretical performance at the expense of practical reliability. They had built tanks that looked magnificent on paper and performed brilliantly in the first 100 kilometers, then broke down and became liabilities. They had convinced themselves that complexity indicated sophistication, when in fact complexity often just meant more ways for things to go wrong. Albert Speer, Hitler's Minister of Armaments and War Production, visited Kummersdorf to inspect the captured Sherman. Photographs show him sitting in the commander's hatch, examining the American tank's interior. One can only imagine what thoughts went through his mind. Speer was an architect by training, a man who understood the relationship between design and function. He could see that the Sherman represented a coherent design philosophy carried through from conception to execution. He also understood, perhaps better than most German officials, that the war was becoming an industrial endurance contest, and that Germany was losing. In early 1943, when these captured Shermans arrived at Kummersdorf, Germany was still winning tactical victories on the Eastern Front. But the strategic situation was deteriorating. Soviet production was recovering and accelerating. American industrial might was just beginning to make itself felt, and German industry, despite Speer's best efforts, couldn't match the output of its enemies. The Sherman wasn't just a tank. It was physical evidence of American industrial philosophy applied to warfare. And that philosophy was brutally simple. Build enough of them, make them reliable enough to keep fighting, and accept that individual technological superiority matters less than collective operational availability. The Germans had 6,000 Panthers. The Americans had 50,000 Shermans. Even if each Panther could theoretically destroy multiple Shermans in combat, and this was far from certain, given the Panther's mechanical unreliability and the Sherman's numerical advantages, the mathematics of attrition warfare favored the side that could keep replacing losses and keep their vehicles running. A Panther tank company with 12 vehicles might start a campaign at full strength. Within 2 weeks, accounting for both combat losses and mechanical failures, that company might be down to 6 operational tanks. Meanwhile, an American tank company that lost 6 Shermans to enemy action could have them replaced within days from the massive supply pipeline stretching back to ports and factories. And the 6 remaining Shermans would almost certainly still be mechanically functional, ready to continue fighting. This was the reality that German engineers at Kummersdorf were documenting, perhaps without fully grasping its implications. They were recording the death of German technical superiority, one measurement and specification at a time. The testing continued through 1943 and into 1944. More captured Shermans arrived at Kummersdorf and at Birka, another German testing facility. The Germans studied them obsessively, looking for weaknesses to exploit. They found some. The Sherman's armor was vulnerable to German tank guns. Its gasoline engines could catch fire when penetrated. Its ammunition storage in early models created catastrophic explosions when hit. But for every weakness they found, they also documented another aspect of American engineering competence: the way components were laid out for easy access, the standardization of parts across models, the quality of welding and assembly, the thoughtfulness of crew accommodations. American tankers had more space, better visibility, more comfortable seating, easier communication between crew members. These weren't tactical advantages in the sense of armor or firepower, but they made crews more effective over long campaigns. A rested crew fought better than an exhausted one. A crew that could communicate clearly made fewer mistakes. A crew that could exit the tank quickly in an emergency had better survival rates. The Americans had thought about these things. They had designed a tank for human beings to operate under stress, not just a mobile gun platform. German tanks, by contrast, were cramped, uncomfortable, and difficult to operate. The Tiger's turret rotation system required the engine to be running at high RPM, which the engine couldn't sustain for long periods without overheating. Panthers had notoriously difficult manual transmissions that required enormous physical strength to shift, fatiguing drivers and increasing the likelihood of mechanical failure from operator error. Both tanks had limited visibility compared to Allied designs, making them vulnerable to flanking attacks. These weren't just minor inconveniences. They were operational limitations that degraded combat effectiveness. A German tank crew that was physically exhausted from fighting their own vehicle's mechanical shortcomings was less effective against the enemy. A crew that had to choose between keeping their engine running to operate the turret traverse and conserving fuel for mobility was operating under constraints that Allied crews didn't face. The captured Shermans at Kummersdorf told a story about two different approaches to the same problem. The Germans asked, "How do we build a superior weapon?" The Americans asked, "How do we build a weapon that soldiers can actually use to win battles?" These questions led to fundamentally different engineering solutions. And the terrible irony, the central tragedy of German tank development, was that German engineers were absolutely capable of building reliable, maintainable tanks. The Panzer III and Panzer IVs, Germany's workhorse tanks from the early war period, were reasonably reliable by the standards of the time. They weren't as reliable as Shermans, but they were functional, repairable, and produced in sufficient numbers to be effective. The Germans could have continued developing these existing designs, incrementally improving their armor and firepower while maintaining their basic reliability. Instead, they chased technical perfection with the Panther and Tiger, creating vehicles that were magnificent in theory and problematic in practice. Some of this was Hitler's fault. The Führer had a fascination with super weapons and gigantic projects. He pushed for bigger guns, thicker armor, more powerful engines. He wanted tanks that would psychologically dominate the battlefield, that would strike fear into enemy hearts through sheer technological superiority. The Panther and Tiger fulfilled this vision. They were impressive, intimidating, powerful. They were also expensive, complicated, and unreliable. But by the time this became clear, Germany had committed its industrial resources to these designs. Factories had been retooled, supply chains had been established. Changing course would have meant months of lost production at a time when Germany desperately needed every tank it could build. So they kept building Panthers that broke down, Tigers that couldn't be repaired in the field, and King Tigers that were so mechanically fragile and resource-intensive that only 492 were ever completed. Meanwhile, American factories were producing Shermans at a rate of thousands per month, creating an overwhelming material advantage that no amount of German tactical skill could overcome. The engineers at Kummersdorf understood the technical realities. Whether they understood the strategic implications is less clear. They were specialists, focused on components and specifications. They could document that the Sherman's transmission was more reliable than the Panther's. They could measure that the Sherman's engine was easier to replace. They could note that American crews performed maintenance tasks that would require German crews to send their vehicles to rear area workshops. But could they see that these technical facts added up to a strategic catastrophe? That Germany was losing the war not because its soldiers lacked courage or skill, but because its engineers had optimized for the wrong things? That technological sophistication without operational reliability was just expensive failure? Some probably did see it. Engineers are, by nature, rational people who understand cause and effect. They could extrapolate from the data. If Panthers broke down more often than Shermans, and took longer to repair, and required more specialized maintenance, then over time the Americans would have more operational tanks. More operational tanks meant more firepower on the battlefield. More firepower meant winning engagements. Winning engagements meant advancing. Advancing meant eventually reaching Berlin. The mathematics were inescapable, even if the implications were too terrible to speak aloud. By 1944, captured Shermans were being pressed into German service out of sheer desperation. 4. German divisions formed captured tank units that included significant numbers of Shermans. The 10th SS Panzer Division operated a separate unit of 10 Shermans at one point. During the Battle of the Bulge, German forces used captured Shermans in deception operations, approaching American roadblocks in vehicles that looked friendly until they opened fire. In the final days of the war, as the Red Army closed in on Berlin, Kummersdorf itself became a battlefield. The various captured tanks still at the facility, Shermans, T-34s, Churchills, were pressed into service by ad hoc German units desperately trying to stop the Soviet advance. Some of these captured vehicles fought alongside German armor. The Sherman that had been tested so extensively in 1943, analyzed and measured and documented, may well have ended its service fighting against its own countrymen in the ruins of the Third Reich. The irony would have been perfect if it weren't so tragic. What the German engineers at Kummersdorf had discovered, in the cold language of technical specifications and test results, was a fundamental truth about industrial warfare. Reliability defeats sophistication, consistently defeats occasionally, and good enough in large numbers defeats perfect in small numbers. The Sherman wasn't a perfect tank. It had real flaws. Early models caught fire too easily when penetrated, earning the grim nickname Ronson after a cigarette lighter that advertised lights every time. The 75mm gun, while adequate for infantry support and fighting medium tanks, struggled against heavy German armor. The relatively thin armor made it vulnerable in tank versus tank combat against Panthers and Tigers. American tankers knew these flaws intimately. They understood that in a one-on-one engagement with a Panther or Tiger, they were at a serious disadvantage. Some referred to their Shermans as death traps. The experience of seeing your shells bounce off a Tiger's frontal armor, while knowing that his next shot would likely penetrate your own, was psychologically devastating. But these individual tactical disadvantages existed within a larger strategic context that heavily favored the Sherman. For every engagement where a Panther destroyed multiple Shermans, there were dozens of engagements where Shermans didn't face Panthers at all because those Panthers had broken down on the road march. For every Tiger that dominated a battlefield, there were 5 Tigers sitting in rear areas awaiting parts or specialized maintenance. The Americans could afford losses because they could replace them. More importantly, they designed their entire armored warfare system around the assumption of losses. Replacement crews were trained and ready. Replacement tanks were in the supply pipeline. Maintenance protocols were standardized so that crews could keep their vehicles running even under difficult conditions. The Sherman was part of an ecosystem designed for sustained warfare, not individual engagements. The Germans, conversely, built tanks for the battle they wished they were fighting. Short, decisive campaigns where technical superiority would lead to quick victories. They designed for breakthrough operations and encirclements, for the kind of warfare that had worked so brilliantly in 1940 and 1941. But by 1943, the war had become an attritional slog, where the side with more tanks, more supplies, and more industrial capacity would inevitably win. The Panther was a beautiful answer to the wrong question. A comparative test conducted in the Po Valley in Italy during March of 1945, just weeks before Germany's surrender, perfectly illustrated the fundamental difference between German and American design philosophy. British forces ran mud-crossing trials, pitting a Panther against various Sherman models and a Churchill tank. The Panther, with its wide tracks and sophisticated suspension system, should have excelled. On paper, its ground pressure was lower than the Sherman's, giving it superior flotation in soft soil. German engineers had spent enormous effort optimizing the interleaved road wheel system for exactly this kind of terrain. Instead, the Panther quickly got stuck in loose soil. When the crew attempted to reverse out of the mud, the transmission broke. The testers couldn't even complete the second part of the trials because they couldn't start the tank. Further analysis revealed that while the Panther's tracks did provide better flotation, the traction was poor, only marginally better than the Sherman's much narrower tracks. All that engineering sophistication, all those carefully designed overlapping road wheels, and the practical performance advantage was negligible. Meanwhile, the Shermans completed the trials. They weren't elegant. They weren't sophisticated. They just worked. This became the epitaph for German tank design. Magnificent in theory, problematic in practice. By the war's end, American factories had produced approximately 50,000 Sherman tanks. These vehicles fought in every theater of the war: North Africa, Italy, France, Germany, the Pacific Islands, Burma. They served with American, British, Canadian, Free French, Polish, and Soviet forces. They were converted into countless specialized variants: tank destroyers, armored recovery vehicles, self-propelled artillery, mine clearers, bridge layers, flamethrower tanks, amphibious assault vehicles. The Sherman's chassis was so reliable and adaptable that it formed the basis for an entire family of armored vehicles, each designed for specific tactical purposes, but all sharing the same basic automotive components. When an M10 Wolverine tank destroyer broke down, you could cannibalize parts from a Sherman to fix it. When an M7 Priest self-propelled howitzer needed a new engine, the same 4 GAA that powered thousands of Sherman tanks would fit. Germany built 6,000 Panthers, 1,800 Tigers, and 492 King Tigers. Combined all German heavy and medium tank production from 1943 to 1945 totaled less than 15% of Sherman production alone. And German tanks, for all their theoretical superiority, spent far more time being repaired than their American counterparts. The final irony came after the war ended. The French army, desperate to rebuild its armored forces, actually continued using Panthers for several years. Not because they were good tanks, but because so many had been abandoned by the Germans in working condition. They'd simply run out of fuel or been unable to retreat fast enough, that France had access to a ready supply. But the French quickly discovered what the Germans had learned the hard way. Panthers were maintenance nightmares. The complicated final drives failed regularly. The transmissions required constant attention. Finding replacement parts for German-specific components was nearly impossible. Within a few years, the French had phased out their Panthers in favor of more reliable designs. The Sherman, conversely, remained in service with various armies around the world for decades. Israel used upgraded Shermans extensively in the 1950s and 60s, re-gunning them with powerful French and British weapons that the original designers had never imagined. The robust chassis and reliable automotive components could handle the additional weight and stress. Israeli Sherman variants fought in the 1948 Arab-Israeli War, the Suez Crisis, and the Six-Day War, more than 20 years after the tank's initial introduction. That's the difference between a tank designed for reliability and a tank designed for theoretical perfection. One keeps fighting long after its designers expected. The other breaks down before it reaches the battlefield. The story of the engineers at Kummersdorf testing captured Shermans is ultimately a story about humility and hubris. The Germans entered the war convinced of their technological superiority, certain that their engineering excellence would translate to military victory. They built tanks that embodied this confidence, powerful, sophisticated, technologically advanced vehicles that represented the cutting edge of armored warfare. The Americans entered the war behind in tank development, scrambling to catch up with European powers that had spent the 1930s refining their armored doctrines. They built a tank that embodied their industrial philosophy, good enough to fight, simple enough to maintain, reliable enough to keep running, and cheap enough to mass produce. The Germans learned slowly and painfully that wars are won by logistics as much as by tactics, that the tank which runs is better than the tank which doesn't, regardless of how impressive the non-running tank looks on paper. That complexity is not the same as sophistication, and that reliability is itself a form of technical excellence. They learned these lessons at Kummersdorf, in the antiseptic environment of a proving ground where captured American tanks could be measured and tested without the chaos of combat. They learned it again on the Eastern Front, when Panthers broke down during road marches and had to be abandoned for lack of recovery vehicles. They learned it in Normandy when Tiger companies started offensives with 12 tanks and ended them with 3 operational vehicles. They learned it in the final desperate battles around Berlin, when mechanics cannibalized 5 broken tanks to keep one fighting. But they learned these lessons too late to change the outcome. The Sherman tank represented American industrial democracy applied to warfare, the arsenal of democracy made manifest in steel and gasoline. It wasn't the best tank in any single category. It was simply the best tank for the kind of war that actually occurred. A global, multi-year campaign of attrition, where keeping your equipment running mattered more than having the most powerful gun. German engineers testing captured Shermans at Kummersdorf in 1943 documented all of this in their technical reports. They noted the reliability, the ease of maintenance, the thoughtful design for field repairs. They measured every component, analyzed every system, and filed their findings with characteristic German thoroughness. Whether anyone in the German military leadership paid attention to these reports is another question. By 1943, Germany was committed to its path, building expensive, complex, powerful tanks in numbers insufficient to replace combat losses. The engineers at Kummersdorf could document American superiority in automotive reliability, but they couldn't change German industrial policy or design philosophy. So the testing continued, the reports were filed, and the war ground on toward its inevitable conclusion. The Sherman kept running, kept fighting, kept advancing across France and into Germany itself. The Panther kept breaking down, kept requiring repairs that couldn't be completed in the field, kept disappointing crews who had been promised invincibility. In the end, the tanks that were designed to be merely good enough proved to be exactly what was needed. And the tanks that were designed to be perfect proved to be perfectly useless when they wouldn't start. The engineers at Kummersdorf had discovered this truth, had measured it, and quantified it, and documented it in meticulous detail. They had opened up the Sherman and found not crude American engineering, but a different kind of sophistication. The sophistication of system thinking, of designing for actual conditions rather than ideal ones, of prioritizing what mattered over what impressed. They had found, in the unglamorous reality of American pragmatism, a rebuke to everything they thought they knew about engineering excellence. And they had found it too. Late to matter. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.